Ну-ка, проверим.
Сейчас проверим. Пока что ничего не запустилось.
Ну, слот хотя бы есть?
Да, слот есть.
Ага. Так.
Вот сейчас, кажется, пошла трансляция.
Ну, буквы есть, да? So, today we shall discuss, continue discussing associated primary decomposition, but actually we have just gave the following definitions, so let us recall them. So now we start with A is a ring, so and M is a module. So later, at some point, we shall require that M is Noetherian, and A is also Noetherian. Yeah, so, but the beginning of the story, so you shouldn't assume, you shouldn't make these assumptions. So we shall be interested in the following object, which is the set of associated primes, so that is a subset of spectrum. Yeah, so such that there exists an element M in M such that annihilator of this element, so precisely the elements that from the ring that annihilates this element M is just this prime ideal P. Yes, so and also we have introduced the support of M, and which is the following, so that is the set of also prime ideals of A, so such that localization of M under this ideal with respect to the multiplicative system, which is a complement to this ideal, is not empty, non-zero. So notice that, so also we're considering the supports with so the module with respect to the ring. So notice that on previous class we have considered different, so we gave examples where the set of associated primes is different whenever you consider one type of the ring or the other. And when you are consider, so it is so notice, so we can also reformulate that associate, so that the ideal belongs to the set of associated primes if and only if there exists an inclusion of E mod P inside M. And of course this inclusion is given by mapping A to A times M, where so if you take the image of the unit, so clearly the unit in AP is annihilated by multiplication by P, so we can consider AP as two different things. So you can consider AP as A module or AP as AP module. And of course, when you are considering AP as AP module, multiplication by A doesn't have kernel, it has zero, because A mod P is domain, it doesn't have zero divisors. Yeah? And if you consider it as A module, of course the unit has an annihilator, and this is precisely P. Yeah, so and you map A to AM, yeah, so that and this gives you annihilator of that element of M is precisely P, and this provides you this embedding, and vice versa. Yeah, so you take the image under this inclusion, and M is just I of unit. Yeah? Just I of unit in the ring A mod P.
Сейчас, а вот там вот МП не равно нулю, это М с индексом?
M, ну, в смысле, это обозначение локализации. Да? Ну, по дополнению, ну, у нас есть мультипликативное, ну, давайте напомню, что МП, да, это следующее, это МС, где S это мультипликативная система, процедура локализации, и S это дополнение до А без P, потому что локализовать в P глупо, там 0 есть всегда, да, поэтому, ну, я имею в виду локализовать по мультипликативной системе, связанной с идеалом P, глупо. Ну, в смысле, не связанной с идеалом P, а вот в точности по мультипликативной системе, состоящей из элементов P. Поэтому это вот как бы недостаток неких обозначений, но он как бы объясняется тем, что просто вот это вот не имеет смысла, если вы это неправильно понимаете. То есть, ну, сама операция. Вот, соответственно, so if you have this inclusion, notice that localization, if you have the sequence of modules, so and localization, which is exact, so the sequence is exact, yeah, so that M3 is just a quotient of M2 by the image of M1, yeah, so that you and M1 is there is inclusion in M2, so this means that the sequence, if you localize, is also exact. And in particular, that if you have inclusions of modules, then you have, so this is exact. So if you have these inclusions of modules, AP inclusion in M, so you can localize with respect to P, so that you have, when you localize, you have non-trivial inclusion into MP. And this tells you, of course, so this inclusion, this implies that MP is not empty. So the support contains the set of associated devices. Prime, so associated prime ideas. So also notice that what we shall prove later, that these sets are quite different. I mean, it is very rare that they coincide, and when they really coincide, it is, you should not note that it is very, very special situation. And yeah, so maybe I shall give a problem, so to ask when they can coincide. Yeah, so usually, so when the module M is finitely generated, we shall notice that this subset is finite, and so let me draw it as a remark. We shall prove that this subset, this set is finite. And this is usually infinite. And notice that if you have, let us notice that if you have multiplicative system S, which is generated by S1 and S2, so multiplicative system generated by S1 and S2. If you take localization with respect to S1 and then S2, so it is the same as taking localization with respect to S. Yes, so and notice that if you have inclusion of two ideals, of two prime ideals, so P is inside Q, yes, so multiplicative system of P is larger. Yeah, so you have opposite inclusion, of course, when you consider complements and this multiplicative system. So this can be plus 1 SP, and this is SQ. And when you take localization, this implies that when you take localization of M with respect to the larger multiplicative system, yeah, so that now with respect to P, you can view it as if you have taken the localization with respect to Q, and then you can apply this operation, localization with respect to P. This implies that if MP is not 0, yes, so that then MQ is not 0. Yeah? So this means that if P belongs to the support of the module, then Q also belongs to the support. So you notice that if you have a prime ideal, yeah, so if your module contains the prime ideal in the support, it contains all maximal ideals that contain this module. So it is one should give this geometric example. So example to illustrate difference between associated primes and the elements of the support. So you can take k x y on the plane and take it modulo x and consider, so this will be a modulo m, and the A will be, of course, the full polynomial ring. So into variables. So you have the line x equal to 0, and now you notice that x is a prime divisor or prime ideal. Why? X is prime ideal.
Ну, если элемент лежит в нем, то можно вынести множитель x.
Не, ну это долго. Проще сказать Да, просто здесь обычно очень, so usually it is very easy to calculate the ring of functions, and it is just k of y, which has no zero divisors. So here there are no zero divisors as in the ring. Yeah, because from the viewpoint of module, notice it has elements that are annihilated. So, for example, by X, it annihilates all elements. But it has no zero devices as the ring. So then X is prime. And you see that, so exactly here you see that, notice that since it has no zero devices as the ring, yeah, so that also X is annihilator of any element in this ring. So it is annihilator of any M that M belongs to K of Y. So this the set of associated primes of M consists precisely of yeah. So here also notice also that for any element of K of Y there is an element that really annihilates it. Yeah, so that any element of K of Y is annihilated by some element. You see that the zero is not in the set of associated devices, because I mean there are no elements where zero is precisely the annihilator, and so the annihilator is the set of associated devices is precisely X. Yeah? And if you look at the elements in the support, yeah, so you notice that you have to include the X in the support, but also if you take any maximal ideal that contains X or any ideal that any prime ideal that contains X, and in this situation they will be all maximal, and they will correspond to the points on this line. Yes, so notice that this will be ideal y minus generated by y minus a and x. Yeah, and this will give you the set of other ideals that will belong to the support. So this will be left as an exercise to establish this. But notice that here the set is finite, and here it is example that the set is infinite. Okay? So the set of in the support. And geometrically, so this is a usual situation, so that if you think about the following situation, so for M, we can put the ring. So if you start with ideal, you can take A mod I and more or less just associate prime devices. It is the set. So it will be more or less the set of. This is not of the set of irreducible components. And plus something else, which is finite. I shall specify what do I mean, but it will require just some time for this. And the support of AM is more just the set of irreducible varieties of irreducible Separators contained contained in the zero set of I. In the zero set. So this is yeah, so more or less. So this is geometric interpretation. That should be kept in mind when you're thinking about these notions. Хорошо? And later we shall understand what I really need. So what I really mean by that is something else, and how different it is, and also so we shall have a theorem that really will tell you that the supportive family will be the set of the separators. So this will be more or less little. So okay, so let us start with the following theorem, that following proposition that is one of the most important parts of the theory, and this proposition tells you that the set of suppose A is Noetherian, then the set of associated primes of M is non-M. So this could be quite funny, but it is one of the most important one of the most important. This is the starting point of the theory, and in fact, it will be one of the most important propositions for the theory. However, this is yeah, and also we should recall the method of the proof. So just this just this will be just so proof will give so remark. The proof will give you the following. So for any element M inside the module M, yeah. So we shall find the element M tilde in A times M, so such that the annihilator of M tilde is prime ideal. So notice that this in particular, this tells you that just given any element or in the submodule, we also can find in this submodule so the element which is annihilated by some prime idea. So this is quite just important for our further discussion. So let us я просто сейчас страниц все могу. So let me notice the following. So we shall the idea is the following. So if you have annihilator of M, some element M, so given E, so such that A times M is non-zero, this will, so you can consider annihilator by the bigger of the element of AM, and of course, so this is so this holds in a commutative world. Yeah, so you see that annihilator, if you multiply annihilator by A, sorry, if you multiply the element of the module by A, then clearly annihilator will be larger. Yes, so since B times M is equal to 0 implies A times M equal to 0. Notice that here this is a subject of commutative. Yes, so because we want to move B here. And this implies that you can think of increasing sequence of modules. And this sequence, yeah, so notice that, yeah, so in order to be able to find an element A2, yes, so that just, so if annihilator of A is not equal to A itself, yeah, so that this implies that there exists A2 such that A1, A2M is not equal to 0, so you can consider this increasing sequence of modules. Or you may think of, yeah, so you may think of the considering the chains of such modules, and you can consider the maximal elements in the chain. Yes, so we can consider chains of this type, this form. And notice that such chains has maximal elements, so since we assume that A is Noetherian and these are ideals in A, yes, so these are ideals in A. So such chains, they have maximal element. So by Noetherian property, A is Noetherian. Then this chain stabilizes. Yeah, so this is just not a Noetherian property, but so that any chain in the ring A stabilizes. But then you can find if you have this property, then by its own lemma, so that you can find, we can find maximal element in the set of the form annihilators of AM. Yes, so just because that if you cannot find the maximal element, then you will have the element A2. You can include it in this chain, and you can enlarge this chain, and this chain will be just will stabilize at some point, and so the largest, if so, not possibility of so saying that we are constructing this chain unless we can find a new element that there will be a larger annihilator, then it will tell you that the last element, when we start stabilizing in the chain, then this is the largest, the maximal element. So notice that third lemma is not applicable here for the just for the following rather silly reason. So that whenever you start drawing a chain of just annihilators of the elements, yeah, so M1, M2, etc. In the end of the day, you have to, so in order for third lemma to work, you have to take the union of these annihilators. And yeah, so notice that third lemma, just let me say, so the warning.
Union not have such form.
Ну да, то есть правильно, вот тут как бы подсказывает, that if you are just starting with considering annihilators, yes, so of the elements, so yes, so and then in order to apply third lemma, you have to just take be able to take the union. And you should find, in order to third lemma to work, you should have, you should write this ideal as in the form of the ideals that you put in your set, and that means that you should find an element M in your module such that. This union is this element of the form, and it is not clear how to find this element. Yeah, so, in general, not clear how to find M. Yeah, because you do not have a limit, yes, in your module, yeah, so you do not have a limit procedure. So, or something else. So, that means that it is tempting to use third lemma as just it is in general, but you cannot do it. So, you avoid it by just considering Noetherian property and looking at, so at least so this means that any chain has maximal element, and this implies now you can apply the third lemma and formula, and you will have a maximal element in the chain. Or you may think it just in a very, very algorithmic way. You just take a new element, as I said, that doesn't annihilate your element on the previous step, and you proceed until you cannot enlarge the chain of this chain by this procedure. And claim is that maximal element in this chain, so maximal element is a prime ideal. So claim that maximal element of the form annihilator of M is prime ideal. So let me prove it. Yes, so that means that so suppose you start with A. Well, let me start with B, which is not in the annihilator, and assume that AB is inside the annihilator. Yeah, so we should prove then that A belongs to B. So we need to prove that A belongs to annihilator. And of course, so notice that, so B is not the annihilator, so that means Bm is not a zero element. So this implies by previous observation that the annihilator of M is contained in the annihilator of Bm. And this implies so this is contained in the annihilator of Bm, and this implies that so this is maximal element. So algorithmically, yeah, so that means that if you have such B, then and we can enlarge the chain, then we proceed, and our element is we proceed until we cannot do this. Yeah, so and this implies that annihilator of M is equal to annihilator of Bm. And also notice that A is inside AB is in the annihilator of M. Yeah, so this implies that A times Bm is equal to 0, and this implies that A belongs to annihilator of Bm. And of course, this is now annihilator of M. So that proves the claim. Yeah? So this is quite easy, and this really explains us. So let me just draw the example. So example of applying this algorithm. Yes, so you can consider the module. So Z mod. So let me just we can take Pn Z or Z P and Q M Z, where P and Q are prime numbers. And notice that so you can start. So for example, you can take this one and take a unit here. Yeah. So annihilator of the unit is what? P to the power n. It is not prime ideal. Yeah? So then just you may think about, so you can take a unit, you can multiply it by invertible element, but if you multiply by invertible element, annihilator won't be changed. And so here you see the example of the chain. For example, you start multiplying by invertible elements, and you see the example of the chain that already stabilizes, but it doesn't stabilize on the maximal element. But then you realize that you can multiply by P, and then annihilator of P will be a larger ideal. Yeah. So this will be P to the power n minus 1. And you start doing this, yes, so until you stop at the annihilator of P to the power n minus 1. And the annihilator will be precisely P, and this is maximal ideal, I suppose. And also, yeah, so you can do the same trick in P and Qn. Yeah, so you can multiply them by several. So you can start with unit, start multiplying it, and but here, yeah, so you will just stop at the following, yeah, so that if you think so, you can take annihilator of Pn minus 1 and Qm minus 1, yeah, so this will be a what? Annihilator of this thing is what?
O.
PQ, yeah? M minus 1 and M minus 1, PQ. And then the trick is that here there are two chains starting by these elements. You can either multiply by P or you can multiply by Q. So this can be, you can stop at annihilator of this form, which is just Q, and you can stop at the annihilator of this form, which is just P. Yeah, so you see that this algorithm, it is quite convenient, and clearly it gives you how you can find this out. So then the next step is just yeah. So yeah. So let me speak about the next step is the following. So one of the most important procedure in algebraic geometry and as well as in commutative algebra is passing to the open set, so it is localization. So the question is what happens when we localize. I mean, can you describe, yeah, so you have a module, so you have a ring and a module. So what will happen when you pass to the localization? So S is multiplicative set. So what happens when you localize with respect the set? How you can describe the corresponding elements, and the claim is that the following, that just when you want to localize, you just have to intersect your so of course we know that when you localize the spectrum, yes, so the spectrum of localization, you can think of this as a subset of the prime ideals by just it is identified with the set of prime ideals in the spectrum such that P intersection with S is empty. Yeah? So you can put the spectrum as the subset. And of course, so when you start calculating associated primes, yes, so that you just have to intersect the support with the corresponding spectrum of yes, and the set of associated primes is is also is intersector with AS. And yeah, so what is non-trivial about this thing? Yeah, so that yeah, so notice, yeah, so just remember. So the idea is just to for the following, so that when you when you're thinking about the spectrum of the support or the set of associated primes or the support, you have collection of prime ideals, and then you just have the subset which corresponds to this multiplicative system. So this is a set of hyperplanes. And your prime ideals, of course, can be contained in this hyperplane, so that the ideals that belong either to the support of the module or the set of associated primes, and you just have to throw them away and keep the previous thing. So, yeah, so the claim about support is more or less evident. I want to just notice that if you have, so note that so if you have A mod P, yeah, so if you have this inclusion, yeah, in M, yeah, so what can happen when we localize? When we localize, so yeah, so you have inclusion, and of course you have A mod P localized, which is just it is just localization, and this is just P is just so P is mapped as P times AS. Негатив черточки нет. And then you have inclusion of this set in the localization. Yeah? So this implies that if you have this inclusion, then you have also this inclusion, but of course there could be a trivial thing here. Yeah, so, ну, что тут вот плохого может произойти вот с этим включением? Ну, как бы мы же подразумеваем, что А-фактор по P нетривиальный, правильно? Вот.
Вернее, его локализация.
Ну, я имею в виду, когда мы определяем ну, именно множество ассоциированных примарных идеалов, мы все-таки считаем, что вот это вложение А-фактор по P это нетривиальное кольцо, потому что P не совпадает с А. Да, и поэтому как бы здесь может произойти что плохого, что.
Ну, просто в ноль все отправится.
Ну да, что вот это вот равно нулю, поскольку so, the bad thing that can happen here that this is so you have inclusion, but technically this bad thing can happen. Only bad thing can happen that really PAS is just AS. So that this means that A mod PS is just 0. Yeah? So in this case, this is 0, but luckily this is the case. So this is the case that P is not So P is not in the spectrum of AS, and this is the case when P intersection of P and S is not empty. Yeah? So this implies that, of course, that annihilate of so the set of associated prime devices, it sits inside intersection of associated prime devices of the localization and the spectrum of AS. This is more or less automatic, but what is not automatic, yeah, so that of course in MS there are more elements than in M, so it can happen that so let us prove the converse inclusion. Yes, so that suppose that P belongs to the spectrum. So the set of associated prime divisors. Oh, sorry, I have just I have. Yes, sorry, just. Нет, тут как бы. Сейчас, я не там пересечение написал, потому что надо
Да,
пересекать.
наверное, слева
Да,
ассоциированные в...
да. И наоборот. То есть, как бы, вот это содержит, да, это множество может быть больше. Я тут совсем все включения на вход. То есть, вот оно больше и содержит пересечение. Ну, как бы мы показали, что любое отсюда, который принадлежит спектру АС, дает нетривиальный элемент вот здесь. Вот, ну, теперь как бы, so now let us see that now assume that you have an element of, so P tilde is an element of MS. Yeah? So you can take and suppose you have natural inclusion, natural map under localization, and yeah, so you can take, so we have to prove that in inverse of P tilde, which is a prime ideal, it belongs to the set of associated ideals of M, and notice that different PIs give different elements in the, so different.
А, кстати, вот еще
Да.
один вопрос про строчку с этим включением.
Да.
Мы же справа пересекаем множество элементов, ну, можно сказать, идеалов
Не, ну
МС
тут,
и множество идеалов
да, ну, сейчас я скажу. Ну тут правильно же понимать, что
то есть это тоже пропускается через это включение.
нет, ну правильно понимать, что АС, да, оно может быть реализовано как есть биекция между АС и подмножеством в спектре А. Да? И вот эта биекция строится так: вы берете те элементы из А, которые не пересекаются с S.
Ну, да.
Да. Ну, то есть, как бы формально говоря, это вот как бы то, что я здесь.
Только, наверное,
Да,
между
вот,
спектром АС и спектром.
ну да. Ну вот я специально тут как бы заметьте.
Да, все.
Да, но да, я тут опять же, ну, как бы, тут именно что, ну, вот в этом месте тут есть биекция, да, то есть спектр S отображается в подмножество. То есть, как бы, правильно говорить, что тут есть отображение, да. Ну и отображение делается так, чтобы P тильда сопоставляете p, которое равно и в минус 1 от p. Да? Тильда. То есть, как бы, и тогда вы, и обратно вы можете, имея идеал p, у вас есть обратное отображение p. Причем, как бы, вот эта биекция, она сохраняет вложение. То есть, если было два разных идеала, они отправились в два разных. So, bijection.
Не два разных, а два вложенных.
Два вложенных, да. Ну и два вложенных, строго вложенных. В смысле, тут важно, что, ну, как бы вложение более-менее очевидно, важно, что строго вложенные, то есть, что они, если были неравны, то и остались
Ну,
неравны.
потому что это биекция.
Да. So this is bijection preserving code. So yeah, so notice that so that was precisely different ideals correspond to different ideals. On this map, and so you have to prove only that this is a subset of associated primes, and notice that so that means that you have an element m tilde that belongs to ms, and so such that annihilator of p tilde, annihilator of m tilde is just p tilde. But what is the problem here? Yes, so that there are two problems. Yeah. So first problem is m tilde is not the element of m. Yeah, so just a problem. M tilde is not the element of M, and problem 2 that annihilate that A belongs to annihilator of M tilde in AS does not imply, even if you take m tilde, so if you take m tilde that belongs to M and consider m divided, so just which is m divided by 1, yeah, so if you just take m tilde already in M and map it, just if you take m that belongs to M and put m tilde to be m divided by 1 inside localization. Yes, so that A belongs to annihilator does not imply that A belongs to annihilator of A inside of M. Yeah? So and now let us just fix this. Yeah, so how we can fix that m tilde is not an M? Just by multiplication. Yeah, so that just m tilde.
Sir,
Да.
it could be AS, right? Like
Что?
there. No.
Where?
On your left. Yes.
This, yeah. So, thanks. Thank you. Yeah, so, if m tilde belongs to ms, yeah, so we can multiply by s, and assume that S M tilde already belongs to M. Yeah, so I shall write it. Yeah, so just we can consider. So I hope you will just forgive me by this, by not saying precisely that M tilde is just, so this is an element of the form M divided by 1. And then you assume this and notice that, note that since S is invertible, the annihilator is not changed in AS. So we do not have to bother about this issue. So first problem is solved. So what about the second problem? The second problem is a little bit technical. It is a little bit more involved because AS, I mean, without any assumptions, the second problem can be solved. I mean, without any, I mean, if you are thinking about arbitrary module and a ring. So if you take AM is equal to 0 in MS, yeah. So this is equivalent, if I don't leave, there exists S that depends on A, so such that SE times A times M is equal to 0. Yeah, so the element is equal to 0 in the localization. If and only if you can multiply it by some element of the multiplicative system S that belongs to S. Yeah? So such that, and I emphasize by the notation that this depends on A. Depend on A. Yeah? So, so this is slight, of course, yeah, so of course in M tilde we can think about taking SA times M, but SA now depends on all elements, and in order to calculate annihilator, then you have to do it for all elements of the prime ideal. Yes, so when you so the idea is, I mean, just not to spoil the condition of taking A times M and having this condition. So notice that we take now preimage of our P. It is a P tilde. It is ideal inside A. A is Noetherian. And this means that I inverse of P tilde is finitely generated. So you have to find the element exactly in the module M, so such that it will be just we have to find. So what is the problem? That when you consider even this M tilde, now we have changed M tilde, so such that it is in our module. So the problem is that even if you take the element inside P, it now doesn't annihilate the module. But now we shall change M again in order that M tilde again, in order that it will be annihilated by this preimage inside M. So we have to change M tilde, so in a way, that it is annihilated by all elements by all elements from inverse of P, and this is done as follows. So so this is finitely generated ideal by A1 AN. So you pick up SI, pick SIs such that. So again, we are applying this thing. Yeah, so just now P tilde is annihilator. So they are contained all in P tilde, which is annihilator of M tilde, yeah, inside AS. So that means that you can pick up SIs such that I times SIM is equal to 0. Yeah, and of course, yeah, so this means that you can pick up common S, put S equal to S1 Si, so S1 Sn, and this implies that AI times M times S is equal to 0. But notice that S, so this implies that notice again, AS is invertible. So just so annihilator. So annihilator in AS of M tilde is just equal to annihilator of AS of M tilde times S. And notice so that if you take now annihilator of just of this new element M tilde S, it will contain, on one hand it will contain I inverse of E tilde, yeah? So by this assumption, yeah? By construction. But notice that just that annihilator cannot so it contains, but it cannot be larger. So it cannot be larger than annihilator in AS intersection of of MS intersection with pre-image of so you can think of the elements that lies in the image, yeah, so that you can think of the elements of A and consider S as A module, yeah, so that means that if you look at the elements that annihilate, you can take the elements M as the element of M. And if you study annihilator, then you should have A modulo M. And you can consider this equality as the equality in AS. Yes, so that you can consider this as an equality in MS and AS. So this means that A annihilates M and should belong to this annihilator. But this annihilator is precisely p tilde, and we are considering the elements, yes, so that are in p tilde and are comes from the image of A. So they are precisely of the form of I inverse of p tilde. So this implies that just next. Yeah, so this implies that annihilator is precisely A in A is equal to I inverse of P tilde.
Окей.
Так, что у нас со временем? Yeah, so, сейчас у нас прям перерыв. Давайте сделаем перерыв, вот после этого я применю вот эти вот два замечания и покажу, что множество ассоциированных идеалов всегда не пусто. Давайте проверим. Да, сюда. Сейчас что-то 20 градусов, 23, что ли, на завтра обещали.
Зато потом через 2 дня опять.
Опять
6.
Ну да.
Непонятно, убирать зимнюю куртку или не убирать.
Ага. Ну что, давайте продолжим. Да, ну, so now let us derive the following proposition that will be precisely characterization of the set of the support and the set of associated prime devices. Proposition. So first of all, which is most important, the set of associated prime devices is not empty. And the second, and actually we shall derive the first thing out of the second, also out of the second, that the set of minimal prime devices of support coincide with the set of minimal prime devices of the set of associated primes. So and of associated prime devices of M, prime ideals of M coincide. prime ideals. I'm sorry, this is.
Should then be material?
Yeah. No, A should, so here A should be nothing.
Okay.
A should be. A is here. Yeah, so first we have proof, yeah, and so we have, just I put this as, yeah, so this is, yeah, maybe I shouldn't say this again. So, just A is my theorem. Yeah, so, and the proof is as follows. So, you notice that, so what happens, so suppose that P is a minimal. Yeah, so notice that this, from the viewpoint of the geometric point of view, so that the set of associated primes, it has several, corresponding to the ideal, so we take A modulo I. And this variety has several components. And now notice that components are ideals of that contain I and are of maximal dimension. And since they are of maximal dimension, from the viewpoint of ideals, they are minimal ideals that contain I. And this the components of you are looking at the components, irreducible components, irreducible varieties that are not contained in so that they are not contained in the other components, and this corresponds to the set of minimal prime ideals, and this is precisely this set. So suppose P belongs to the support of M and is minimal, and P is minimal. What does this mean for our ring? That if you localize, so if you have Q inside the support, so two options can occur. That just Q. So there are two options. Yes, that Q intersection with. Q has elements that has outside of P. So Q intersection with E without P is not empty. Or Q is contained in P. So the first means that Q doesn't belong to, so A mod P is precisely the multiplicative set that will localize. Yeah, so this means that Q is not inside, so cannot gives you ideal, which is when you localize Q, then you will get the whole ring. So the symbol, we can say that Q is not doesn't give you ideal in the spectrum. Yes, so that just maybe I should say that Q times AS is not in the spectrum of AS. Okay? And this is not possible. So since P is minimal, this implies that Q is equal to P. So when we consider the support of the localization of MS and the AS. Yes, so it is equal to it is just equal to P. Because there are so if you localize, yes, so this is intersection of the support with of AS and then with the spectrum of AS, and this is just equal to P. But notice that if you take the set of associated primes of the localization, yeah? This is on one hand that we have proved that this is a set of associated primes that belong to the spectrum. I think of this set again as the set of spectrum, yeah, so that this maybe one should write down that you have to I mean more formally, so let me just do the following. So AP. So you are just you are writing down inclusion of the spectrum of AP. Yeah, so you have just I that is homomorphism of the ring that A maps to A. Its localization. Yeah. And you may think of the induced map of the spectrums. So let us denote it by the same letter, yeah? Or by I sharp. So I shall just write like this. To emphasize that this is a subset of the spectrum of A. And сейчас у меня что-то зависло, секунду. Вот, and you have this, so what is most important here, that you have this set. It is in order to get this set, it is the localization of, so you have to take the set of associated prime ideals and intersect it with the image of the spectrum of IP. But it is contained inside the support of the localization. And the support is equal to P. And what are the options for this set? It is either empty or it is equal to P, but it should not be empty. So since associate we have proved that this is not empty, so the ring A was Noetherian, so localization it was Noetherian. So this implies that the set of associated prime ideal, so this is exactly equal to P, and this implies, of course, the following. So this implies that P is the minimal element in the support. Support is the largest set, so we proved that P is inside the set of associated primes. So we have proved E belongs to associated primes, and there is a minimal element to that. Окей? То есть у нас есть два множества, одно большое носитель, другое множество ассоциированных простых. Мы взяли и ассоциированные простые, они лежат в носителе. Мы взяли минимальные элементы в носителе, и мы показали, что каждый такой элемент, он уже лежит в множестве ассоциированных. Это просто мы как бы посмотрели на него через лупу, да, можно считать, что выбросили все лишние элементы, оказалось, что он там сидит один, и просто потому что множество ассоциированных простых не пусто, да, оно должно уже совпадать вот с этим P. Ну и как бы отсюда следует, что P уже лежит в множестве A. Вот. Ну хорошо. С этим все. So now what about finiteness of the set? So now we shall notice that the set of associated prime divisors is finite. Yes, and this is now on the assumption that M is Noetherian. So M is Noetherian. Then the set of associated prime divisors is finite. And as a corollary, what we get here, that we can, as a corollary for geometry, so we can consider ideal, yeah? And we notice that radical of I, so geometrically the set of points that is defined, it is given by the set of, so it is intersection of prime ideals, where prime ideals belong to, they are, ну тут мы еще кое-что не доказали, давайте это я потом скажу. Давайте это немножко потом. Просто одно еще утверждение мне нужно. То есть как бы вот эта вот теорема, она как раз вот отсюда будет следовать на самом деле, что множество неприводимых компонентов у любого многообразия конечно. Да, то есть это, ну, то есть такое геометрическое уже свойство. Но давайте вот докажем вот это. Yeah, before proving this general statement, we shall prove the proposition. Suppose you have exact sequence, short exact sequence. Then just the set of associated primes of M2 is contained in the union of the set of associated primes of M1 and of M3. Yeah, and the question, yeah, so that question. Is this inclusion is strict? This inclusion is strict. I mean, can we put the quality here or not? That's a lot. Ну, например, кто-нибудь может сразу привести пример? Пример простой. Можно даже с Z. Ну, в смысле, с модулями на Z. Ну, какие вы вообще точные последовательности знаете? Z.
Самая простая P, Z, P фактор. А Z
Да,
P.
да. Ну вот, как бы, ей надо. Вот. Тогда, ну вот, как бы, какое множество здесь ассоциированных идеалов? Ну, что вообще хоть что-то может аннулировать? Но только 0, да, то есть это просто 0. Ну и 0 действительно, у нас есть не делитель нуля 1, и вот 0 его может аннулировать. А что вот здесь? P. И без нуля, да? Вот. Ну и как бы мы видим, что вот тут даже меньше, да, элементов, чем здесь и здесь, да? То есть, когда... Ну, давайте вот это докажем. Это простое утверждение. So let us prove this.
Секунду.
Да.
Первый модуль в последовательности, там разве не z умножить на p должен быть?
Не, ну это как бы можно, это вопрос, что я понимаю под вот этим отображением. Не, ну как бы, ну я же не, ну то есть как бы иногда PZ пишут. Ну как
просто
модуль,
z вложили
но,
умножением на p,
в
да,
смысле,
все.
что вот это вот отображение, это умножение на P, да? Просто, ну это как бы разный стиль, но почему мы используем этот разный стиль? Ну как бы, потому что когда вы говорите PZ, вы сразу вот это отображение пишете, но полезно думать как о PZ, как о модуле. Ну это смешно выглядит, что я так говорю, но это просто бывает более общая ситуация. Полезно думать как о Z, что это модуль непосредственно, который заморфен Z. Ну, то есть, как бы из-за этого вы пишете тут модуль, а тут отображение. То есть, как бы, потому что, ну, например, когда мы считаем на сите тот же множество ассоциированных простых, ну, как бы, его нужно считать, ну, для изоморфных модулей, а не изоморфных. So let us prove this proposition. So, what do we have? So suppose you have M2, yeah? So you have, so here you have to do simply the following. So if you have a P that belongs to the set of associated primes of M2 or M3, yeah, of M2, you should prove that it either belongs to M1 or to M3. Yes, so to the set of associated primes of M1 or M3. So, assume that you have the following, so you have inclusion of A mod P inside the M2. So then you have the following, so assume that, yeah, so let me put this as I, yeah, so assume that I of AP doesn't intersect with the M1. So you can, I mean, intersect only by 0. Then, so let me put it P. So then phi of this thing gives inclusion, because this is precisely the kernel of pi. Yes, so this is equal to the kernel of pi, restriction to I of A mod P. Yeah? So the kernel, so you restrict pi to the submodule, the kernel is 0, and this gives inclusion of A mod P inside M2. So this means that P is in the set of associated ideals of M2. But then, just otherwise, so otherwise, you have non-empty intersection. So and notice, so notice that what property does it have? That if you have element, so you have a unit element in A mod P, yeah, and note that and annihilator of unit. So annihilator of unit in A is equal to P, but A mod P has doesn't have zero divisors. A mod P does not have zero divisors as the ring. Of course, it may happen that A mod P has submodules. For example, you can take maximal ideal containing P. Yeah? So you just take maximal ideals containing P, but A mod P doesn't have, so it doesn't have zero divisors. So this implies that annihilator of X in A mod P is 0, in A mod P, yeah, is 0. And this implies that annihilator of X for X in A mod P. So this means that annihilator of X in AP is equal to P, precisely P. Yeah. So this implies that we can take this element, so take X inside I of AP and M1, yeah, so to get an element X with annihilator equal to P. Yeah? So that means, so to get P equal to annihilator of A inside X tilde, and this implies that P is in the set of associate prime ideals in now in M1. Yeah? То есть вот как бы мы увидели, что so we have seen that the first inclusion of A mod P in M2 doesn't give you inclusion of precisely in this A mod P in M1, but we have considered a submodule in A mod P where with this kind of inclusion, and notice that A mod P is so this is warning from the viewpoint of representation theory. Yeah, that of course. Warning. From the viewpoint of representation theory, A mod P is not simple. Module. Simple module means it doesn't contain any proper submodules. Since if you take M inside P maximal ideal, this implies that M mod P is a submodule in A mod P. So you see that A mod P can be a simple if and only if M is maximal, and in this case A mod P is a field. Simple if P is maximal. And A mod P is a field. It is just to compare these things with representation. And this gives us, so this lemma gives us the following, that you may always bound the set of associated prime devices by the set of associated prime devices of submodule and its quotient. And let us do this procedure, so proof of the proposition of finiteness. Yeah, so assume, so we start with inclusion A mod P. So there exists inclusion. So since so here notice that we have not even to assume that this set is not empty here. Yeah. So because otherwise we do not have a subject of the token of this theorem. Yeah, so just so we have to bound this set. So let me say that so in the statement we do not need Noetherian property of A. A is Noetherian, but only that M is Noetherian. Yeah, so if you have this inclusion, yes, so you can put it equal to M1, and you get the sequence M1, M2, M2 is just M1, M modulo M1. And here you have, yeah, so let me just write it explicitly. So M modulo M1. And here by induction, yeah, so you see that the set of associated primes of M is contained in the set of associated primes of M1, but this is just A mod P, so this is just P. When you take only A mod P, it is clear that the set of associated primes, so notice that the set of associated primes of A mod P is equal to P because all elements have annihilate equal to P. So all elements have such annihilator. Yeah, and the union of the quotient. So we have to bound the elements in the quotient. And here, so if this is not empty, so we can assume that by induction that this is finite, but we cannot because we do not have the property. I mean, we have to use the stabilization property. Yeah, so that just you see that this will give you. So if this set is not empty, is not empty, we can proceed by constructing A mod P2 inclusion in M modulo M1. Yeah, so this will be I2, and you can pick up. Yeah, so let me put it to be P1. Yeah, so we can pick up the module which we denote by M2. It is pre-image of P1 of the image of this module. Yeah, so of I2 of A P2. Yeah, and this will give you the module that contain M1, and you can proceed. Yeah, so that you can this will give you this module of M1, so over module of M1, and of course, yes, so that yes, so we can apply this procedure. So apply procedure to M modulo M2 modulo the image of I of AP2. And more generally, yeah, so that if we have constructed MI, yeah, so we can take just so we see that associated prime ideals of M are associated prime ideals of MI and the quotient. Yeah, so if this set is non-empty, we construct the EI plus EJ plus 1 inclusion of E mod PJ inside. Sorry, let me put the index j here. So in M mod mj, and we have pj mapped from M to M modulo mj, and I'm just doing this this by induction, and so you can put mj plus 1 to be the preimage under pj of the image of I j plus 1 of A mod pj. What you get the sequence of modules M1, M2, etc., Mg, etc., Mn. Yeah, so here we do not even assume that the last module in the sequence is equal to M, so by Noetherian property the sequence stabilizes at Mn, so by Noetherian property this sequence stabilizes. Yeah, so we have the property that pi, A mod pi, is isomorphic to mi plus 1 modulo mi. And also, since Mn is last in the sequence, you see that the set of associated divisors of M modulo Mn is empty. Yeah, so I mean, when A is non-Noetherian, this can happen. Yeah? And this implies that by our previous lemma, yeah, so we get that M is, so the set of associated divisors of M is contained in the union of associated divisors of mi modulo mi minus 1, so which is the union of pi's and is finite. So you have this kind of thing. То есть, ну, достаточно прямое, простое рассуждение, но единственное, что вот нужно вот эту вот цепочку модулей просто аккуратно написать. То есть каждый раз мы берем А-фактор по P, ну, он лежит не в модуле M исходно, а в M по MJ, поэтому мы его должны вернуть. А вот это, ну, как бы вторая теорема гомоморфизма. То есть вот это вот. So this is second theorem on homomorphism. Ну, потому что внутри фактора это, мы взяли А-фактор. Вот, ну, вот такое вот как бы доказательство. То есть это показывает, что уже вот, то множество, с которым мы работаем, конечно, и оно говорит о том, да, что as a corollary we see that, so corollary of two statements that AS and as well as support has finite number of minimal elements. So notice that, of course, now for associated prime devices, it is evident because this is a small set we have proved that. But for the support, this is completely not evident statement because in the support we have many elements. I mean, prime ideals, it is not clear why this set is finite. So, and now I want to pass to geometric statements. So one can consider you can compare annihilator. So suppose the M is finitely generated. So you see, sometimes you need for the constructions and for the statements, sometimes you need the module is finitely generated. Sometimes you need only Noetherian property, and of course they meet in the best way when you are considering all the assumptions. But some of the statements do not really need all the assumptions about the theory. So suppose the M is finitely generated. So here again, this is some kind of assumption that M is finitely generated and A is Noetherian, then you will get that M is Noetherian. Yes, so that. But you can only now assume that M is finitely generated. Then we can calculate the support and compare annihilator of M, or even we can compare radical of the annihilator. So we can take radical of the annihilator, and I claim that it is equal to the intersection of prime ideals such that P is in the support. Yeah, so note that, so proof. So this is some kind of geometric statement.
This will be reversed, right?
Yeah. And the inclusion is, I mean, that just belonging. And also, so notice that since you are taking intersection of prime ideals, so you can take only minimal elements. So just P is minimal. Element in the support. And notice that now, I mean, what is the benefit that this is a finite intersection? Because the minimal elements of the support are finite. So finite intersection. And geometrically, this is precisely our, so let us recall that, even starting proof, but, so recall that radical of I is just the intersection of prime ideals containing I. So this means the following, that when you apply this statement to A mod I, so you can apply this to A mod I, And you see what is the annihilator of this module? It is precisely I here, yeah, because so annihilator of A mod I is I. And if you are speaking about radical, this is precisely what defining the set defining P. And these PIs are just the subsets of so PIs that are containing, so P that contain I, it is irreducible subvarieties of maximal dimension. Of maximal dimension. Yeah, so and what this theorem really states that the number of components is finite. Yeah, so the number of irreducible components is finite. So no. Yeah. So now. So what about the radical of the annihilator? We just have to say the following. So if you have P that you have to say that if P belongs to the support of M, if and only if P contains an annihilator. So we have to prove yeah. So here notice that if what does it mean that P contains an annihilator? So just if P contains an annihilator, yeah, so this means that multiplicative set A mod P does not contain сейчас дайте посмотрю, в какую сторону проще. Да, ну, в эту проще, да. If P contains an annihilator, that means that multiplicative set does not annihilate some element. M inside M. And this gives you non-trivial element in the localization in P. Yeah, so since so non-trivial element, yeah, so since Sm is not, so triviality means Sm is equal to 0 for some S inside S, which is A without P, which is not possible by assumption. Yeah, so which is not possible. Хорошо? То есть в одну сторону это очевидно, да, что если у нас P содержит аннулятор, тогда у нас просто вот это множество не может аннулировать никакой элемент, а значит у вас невозможно вот такое равенство, и это было бы, если бы m был нулем когда мы произвели локализацию. Поэтому нужно доказать в обратную сторону. То есть, so assume that MP is equal to 0. This means that you have a collection of MIs, so these are generators. Of M. And they should be annihilated by some elements when you pass to localization. Yes, so that means just you have Si times Mi is equal to 0 for some Si inside this. Yes, so the problem is that, I mean, if M was infinitely generated, the problem is that each element of M could be annihilated by its own Si. Yeah? So, but since M is finitely generated, so M is finitely generated, so this set is finite, so we can put S equal to S1 as N, and Sm is equal to 0 for Smi for any I, and this implies that Sm is equal to 0 for any M inside the module. And notice that S is in the complement. Yes, so that means that this implies that S1 Sn belongs to the annihilator of M, and in the same time it is not trivial element, because it is a product of elements that doesn't belong to node that S1. Of course, in the ring, when you have 0 divisors, the product, the large product of elements could be 0, but not notice that this is not equal to 0, because since each Si doesn't belong to P, it is an element in the multiplicative set. And this implies that their product is not in P, so in particular they are not 0. Yeah? So we have found a non-trivial element. That is not in the annihilator, and this so we found S that doesn't belong to P, and S is inside annihilator. Yes, so P doesn't contain annihilator. Here does not contain. And vice versa, if P doesn't contain annihilator, we take this element in the multiplicative set, and So if E does not contain annihilator, so take S in the annihilator and not in P. And S annihilate any element of M of the localization. So this means, and it is invertible. Yes, invertible. This means that localization is 0. So this proves the statement about the support annihilate. And now let us move to primary modules. Yes, so that let us study primary modules. So primary submodules. Primary. So let us recall the definition. So the definition looks a little bit strange, but it corresponds to the because it can be formulated purely in terms of the quotient of M and N. So let me put the definition. So N is called primary. N submodule of N is called primary submodule. If you have if for any A inside A for each there exists E. So the M and the quotient. So such that A M is equal to 0, yeah, so in the quotient. This implies that there exists such big N. So there exists nu. So such that the map A mu from that multiplies from Mn to Mn is 0. Is 0. So meaning that if you are, so you have operator. So just in brief words, if you have phi A, which is operator from Mn to Mn, yeah, so that to M you associate 5 M is just equal to A times M. So if kernel of phi a is non-trivial, this implies that the operator is nilpotent. And this can be written in a more brief way. Yes, so let me just write down usual definition. That I mean, nothing. So this is somehow this definition is natural from the viewpoint of formulation for the operators, but in terms of elements, it is not convenient to formulate it like this. It is usually formulated in a more in a shorter way, but it is less conceptual in some sense. So just n is primary. If for any a for which there exists m in M such that M is not in M and A times M is in M, we have, so there exists nu from the natural numbers such that A nu times M sits inside M. То есть, ну вот как бы, видите, ну то есть как бы вот те определения, ну как бы это подлиннее, да, то, что я говорил. Ну вот это вот самое длинное, вот это надо расписывать, что такое ядро и что такое нипотентность. Ну то есть это как бы более заумное, да, в какой-то мере определение. Вот это просто я вот это расписал по больше, да, по длине, но вообще как бы можно было это определение вот записать вот так коротко, но тогда вообще ничего не понятно становится. Ну, то есть как бы непонятно, какую роль вообще, ну, то есть как бы если мы хоть имеем какую-то интуицию об операторах, да, то как бы вот это определение, ну, определение как бы, почему оно правильное и так далее. А это определение говорит о том, что у вас, ну, если оператор является, ну, имеет ядро, то он тут же нипотентен. То есть что, о чем это говорит? Что вот, ну, ваш оператор, вот, ну, вообще говоря, да, когда у вас есть Жорданова форма, то у вас есть, ну, невырожденная часть ну, то есть, которая состоит из Жордановых клеток определенных там с другими собственными значениями, она невырожденная, и есть нипотентная часть из Жордановых клеток, которая отвечает нулям. И вот это вот как бы по сути говорит, что у вас от оператора, вот это свойство, да, говорит о том, что у вас, если у вас не тривиальное, то либо у вас нет части, которая вообще отвечает нипотентам, да, оператор сразу не вырастет. Тогда вот это не выполняется, первое условие, да, вообще на наличие ядра. Либо у вас оказывается, что наоборот нет невырожденной части, есть только вот эта нипотентная часть. То есть это как бы, ну, вот, если думать об операторе в Жордановой форме, это все-таки понятнее, ну, сразу нам как бы, ну, говорит, что можно ожидать от нашего оператора. Yeah, so why these modules are important? Because it happens that they are related with what we are saying. So we can just claim that yes, so the theorem of opposition. Yeah, first of all, a question. Yes, so just a question. That question. So notice that we have, let us recall that, so if you have P is prime, Yeah, so we also have the definition of primary ideal. So notice that primary ideal is the following, that the module A mod Q is, from the viewpoint of the statements, N is primary, so you have primary ideal. These are consistent notions, so A contains Q, and this plays role of course of M, and this plays role of M. And the same primary, that means that there exists an A such that A, B belongs to Q, and A is not in Q. So this tells you that B is and this implies that B is not in Q. So this implies that multiplication by A have non-trivial kernel, from the viewpoint of the previous part. So this implies that A inside nu belongs to Q. So this is precisely saying this thing about nilpotence, because you have unit in this ring. So you have this can be checked as so the property that A nu times A is inside Q can be checked on unit. So is checked on unit. So A nu times 1 belongs to Q. So you see that first of all you see that and this means that B is in the kernel of operator 5A, where 5A is multiplication from A mod Q to A mod Q. So B is not and B is not non-zero element. So that B is not in Q gives you that B is non-zero element. A times B gives you then that an A mod Q A has kernel equal to B, and this implies that A in the power nu is nilpotent operator, meaning that this property and that is restated as just I mean that is so since we have unit, this follows from this equality. So this is precisely the definition of so let me put before the question. Remark: if Q is primary ideal, then the Q is primary as a module of A. So it's primary as a module of A. And so notice that we have we noticed that the radical of Q is prime ideal. So the question is is it true that if radical of Q is prime, then the ideal is primary? So since I know the answer of the question, so that and it is formulated as the question, so you know the answer, This is not true, and I will give you an exercise to provide example. So just exercise will be provide example. This will be clear after some observations, but now it's not so easy exercise. But you have to understand that so it is tempting to say that so we have a P that is associated with Q, but not so this is so that this equality doesn't imply that Q is prime. And the proposition is the following. It is a characterization of being associate primary. So if n in M is primary, then I claim that the set of associated primes consists of one element. So notice that just the second, and this is if and only if. Yeah, so this if the set of associated primes is equal to P, then this implies that n is primary. So this is precisely a characterization. So this is one prime. And this suggests to say that if we have this property, so if you have prime ideal, this give primary module, this gives you uniquely a primary ideal. So this suggests that n is called associated with P. And the last part, you can consider annihilator of the radical of the annihilator. Is equal to precisely P in this case. So, and the annihilator is prime, so that, and the annihilator is primary ideal. Yeah, so you see that, yeah, so this, yeah, so, yeah, maybe it is, so since we have to stop soon, I think it is better to prove this next time, but the only remark we say that n, so here in this situation we say that n is primary ideal, primary submodule associated with P. Also, also, of course, you may ask me about, so in a sense that this definition somehow it is a little bit strange, because all I'm saying is just formulated in terms of the quotient. Yeah? So in a sense, you're speaking, so this is precisely the properties of the quotient, not of the module itself. But the thing is, so why we are calling primary submodule, we're interested in n and not in the quotient. The reason is that you just, the aim is to say that any n is the intersection of some modules that are primary. Yes, so that that's I mean what is when you're speaking about ideals, yes, so we are interested in the saying that I is an intersection of primary ideals. If you're speaking about modules, that means that we are interested in describing n as the intersection of primary submodules of m. So that is the main reason that even if we take into account that we are interested in the quotient, in the properties of quotient, speaking about primary ideals. In a sense, when we are speaking about primary decomposition, we are interested in the submodules of M. So that is the main reason. So this is somehow expository reason, and because we are, in all of these results, we are aiming to decompose N in the intersection. And next time it will be clear, when we will be speaking about this intersection, it will be clear why we're speaking about properties of primary submodules, because we can say something about that intersection. Okay, so thank you. I think